Hi, everybody. My name is Alejandro. I am an associate professor at the Universidad de Zaragoza. The other co-authors of this work are the PhD student Hugo and professors Vicente, Salvador, and Julio, all of them from Universidad Politécnica de Valencia. The main goal of this work is to improve the system performance with the design of an L1 data cache with a much larger storage capacity compared to a typical L1 data cache in current microprocessors. To do so, instead of using traditional SRAM technology to implement the cache, we exploit the recent Racetrack or domain world memory technology. This is the fast-track cache. Current microprocessors usually implement a three-level cache hierarchy. The L3 has a capacity in the order of tens of megabytes to prevent most accesses to reach the costly off-chip memory, but they present a high latency compared to inner cache levels. L3s are traditionally implemented with low-power SRAM technology, although some recent microprocessors from IBM and Intel use EDRAM technology for this cache level. L2 caches are smaller, in the order of hundreds of kilobytes, and have a medium latency. These are also typically implemented with low-power SRAM. Finally, L1 caches reside within the pipeline of the microprocessor, and therefore they are very small, in the order of tens of kilobytes. They are implemented with high performance SRAM and have a low latency to fulfill the pipeline timing constraints. On the other hand, applications demand an ever-increasing amount of memory resources. In the last decades, L1 data caches have grown in size. For instance, the L1 size of Intel Pentium 3, Nehalem, and Skylake is 16, 32, and 48 kilobytes respectively. However, it is difficult to achieve such a growing trend given the constraints of SRAM in terms of latency, energy, and area as the cache size grows. As a motivation for this work, this figure shows the speedup of a hypothetical 160 kilobyte L1 data cache with respect to a two-level cache hierarchy consisting of a 32 kilobyte L1 data cache and a 128 kilobyte L2 cache. That is, 160K is the sum of the L1 and L2 capacities of the two-level cache hierarchy. Results are shown for 5 cache-demanding applications from the Spec CPU benchmark suite. Such a huge cache achieves at least a 30% performance improvement for all these benchmarks. In other words, the two-level cache could be replaced with a single-level cache, largely improving the system performance. However, the latency, energy consumption, and area of a 160 kilobyte SRAM is unacceptable in L1 caches. To overcome these problems, instead of using SRAM, we propose to exploit the Racetrack memory technology, leading to a 160 kilobyte cache with a similar area compared to the original 32 kilobyte SRAM cache, thanks to the storage density of Racetrack memory. This table summarizes the pros and cons of its technology. Racetrack memory is much denser than SRAM and consumes less energy. However, the main problem of Racetrack memory is the variable latency required to access the cache, which has prevented its adoption in L1 caches so far. These are the contents for the rest of the presentation. First, we are going to introduce a background of Racetrack memories, including some design decisions for the proposed fast-track cache, or simply FTC. Then the proposed FTC will be described in detail, followed by the experimental results. Finally, the main conclusions will be drawn. First of all, we are going to see why Racetrack memories have a variable access latency. A racetrack or tape consists of n domains. In the figure, green and gray domains are treated as effective and auxiliary domains. The latter are required to avoid losing data in the edges of the tape. Effective domains have a magnetic polarization, representing either logic 1 or 0. A tape also includes an MTJ header, similarly to STT-RAM memories. The MTJ is used to access the domain under the header. For instance, this is the domain at address 1 in the above figure. In such a case, a read access is as fast as in an SRAM cache. However, accessing another domain not under the header imposes a variable latency because domains require to be shifted in order to position the target domain under the header. The figure below shows the state of the tape after a two-domain write shift required to access the domain at address 3. Read operations using an MTJ header are fast enough. Unfortunately, this is not the case for writes. In racetrack memories, shift-based writes have been proposed to reduce the latency of write operations. This approach includes a couple of domains with fixed logic 0 and 1 values as seen in the figure. Instead of performing a write operation through the header, writes are performed as shifts involving the added domains without header intervention. This table shows a comparison between the typical MTJ-based and shift-based writes. The write latency is improved from 5 to just 2 cycles. In addition, dynamic consumption is also reduced with shift-based writes. However, shift-based writes impose an additional transistor per header, limiting the density of racetrack memories, and imposing a trade-off between number of headers and storage capacity, since the area of racetrack memories is determined by the number of header transistors, but not the racetrack itself. The figure on the right shows the involved transistors in read, write, and shift operations. Reads and writes are controlled by read wordline and write wordline transistors, whereas shifts are performed through the SC transistors. Recently, ring-shaped racetracks have been proposed to eliminate the overhead of auxiliary domains. In this example, a 32-bit ring-shaped racetrack includes 2 headers, each of them with the pair of read and write wordline transistors. Let's see how a read operation is performed in header 0, that is the header at the top left of the racetrack. To read the domain under header 0, the source line SL and bit line BL are connected to 1 and 0 respectively, and the MTJ connects to SL through the read wordline transistor. In this way, the stored value is read through the bitmap. To write a logic 1, SL and BL are connected to 0 and 1 respectively. In this way, current flows from BL to SL through the write wordline transistor, performing a shift of the logic 1 present in the blue domain toward the domain below the header. On the other hand, to write a logic 0, SL and BL are connected to 1 and 0 respectively. In this way, current flows in the other direction, that is, from SL to BL, through the write wordline transistor, performing a shift of the logic 0 present in the red domain toward the domain below the header. Shifts are performed through the SC transistors. Depending on the voltage at SL and BL, current flows in either clockwise or anti-clockwise directions across the tape. In this example, with SL and BL set to 0 and 1 respectively, shifts are performed in clockwise. If values at SL and BL are reversed, shifts are performed in the other direction. An end domain shift usually imposes an end cycle latency penalty. In L1 caches, it is imperative to reduce the shift latency as much as possible. To do so, we exploit the state-of-the-art dynamic lazy header policy. In a multi-header racetrack, the nearest header to the target domain is selected at runtime. In addition, the header remains in the same position after the access completes, which helps exploit temporal locality. In this example, the nearest header to the target green domain is header 1. Therefore, a 1 domain left shift is performed, and header 1 remains above address 4 until the next access is performed. Notice too that with this policy, The maximum shift distance in cycles is the number of domains between consecutive headers divided by 2. In this example, the maximum shift distance is 2 cycles. Now we are going to introduce the proposed FTC design following a bottom-up approach. First, we propose a racetrack memory cell tailored to L1 data caches. Then, this cell is used to implement an FTC module. Finally, modules are combined to implement the cache data array. The challenge when designing a racetrack memory cell for L1 caches is to reduce the access time as much as possible without significantly reducing the storage density of this technology. This figure depicts our proposed cell. Below the 128-bit ring-shaped racetrack, up to 66 transistors can be found. Such a number of transistors implement 32 headers and ensure shifts in both directions. Notice too that the distance between consecutive headers is 4 domains, so the maximum shift distance is only 2 cycles. According to the cell layout, the area is 3510 f to the power of 2, where f is the feature size of the transistors. Taking into account that 1 bit SRAM cell area is 146 f to the power of 2, 20 SRAM cells can be fitted into the area of the proposed cell. That is, the FTC cell is 6.4 times denser than SRAM. Multiple cells can be used to implement FTC modules. In this way, each bit of the proposed cell refers to a different cache line. Taking into account that lines occupy 64 bytes, 512 cells are necessary to implement a module consisting of 128 lines. Notice too that in order to access all the 512 bits of a line simultaneously, shifts in every cell are performed in lockstep. The figure on the right shows how lines can be arranged in a module. A possibility is to sequentially arrange one line after another. However, such a sequential line arrangement does not exploit the spatial locality present in L1 caches. In contrast, we propose a novel header-interleaved line arrangement to minimize the shift penalty, shown in the figure below. In this case, lines from 0 to 31 are under a header, and shifts are not required while accessing such lines. After a one-domain left shift, lines from 32 to 63 are placed under a header, preventing any more shift while accessing them. This figure refers to the shift latency distribution and shows the effectiveness of the proposed header-interleaved line arrangement. Each benchmark in the x-axis includes results for the sequential, or sec, and proposed header-interleaved, or int. 3 categories are shown. The 0 cycle means that the target line is already under the header and no shift is required. 1 cycle and 2 cycle mean that 1 and 2 shifts are required respectively before accessing the line under the head. The proposed header-interleaved increases the 0 cycle category in every benchmark with respect to the sequential approach, leading to an average 0 cycle distribution of 76%. A single module consisting of 128 64-byte lines implement an 8 kilobyte direct math cache. Multiple modules can be combined to implement n-way set-associative caches. For instance, a 128 set two-way cache can be implemented with a couple of modules shown in the figure. One of the modules stores weights 0 for every set, and the other module stores weights 1. Notice too that both modules shift in lockstep to access the 2 ways of the target set at the same time, like in high-performance L1 caches. To implement caches with a larger number of ways and/or sets, modules can be expanded as needed. For instance, a cache with 512 sets can be implemented with 4 columns of modules, each one referring to a different range of sets. Similarly, each way is implemented with a new row of modules. Remark that an access to a given set, for example, the set highlighted in orange color in the leftmost column, does not imply shift in the remaining columns. This exploits the temporal locality present in L1 caches. The organization shown in the figure corresponds to a 160 kilobyte 5-way FTC cache. Notice that this capacity is 5 times the storage capacity of a conventional 32 kilobyte SRAM cache, occupies less area than the conventional cache, and it is the sum of the L1 and L2 capacities for a 32 kilobyte L1 and 128 kilobyte L2 cache hierarchy. This table compares the access time in nanoseconds of different L1 cache configurations, including a 32 kilobyte 4-way conventional SRAM cache, the proposed 160 kilobyte 5-way FTC, and a conventional SRAM cache with the same capacity and number of ways as the FTC. As expected, compared to the 32 SRAM cache, FTC increases the latency of the much larger tag array, which is implemented with SRAM. Similarly, the routing and row decoder latency is slightly increased for the FTC. This is mainly due to FTC requires to multiplex the proper header to the access port of the cache, and FTC includes more sets and ways. On the other hand, the bit lines delay is reduced in the FTC because it occupies a 6% less area than the 32 kilobyte SRAM cache. Overall, the data array access time is roughly the same for both FTC and the conventional 32 kilobyte cache. In contrast, the conventional 160 kilobyte cache substantially increases the routing and bitline delays, leading to a much larger access time. The experimental results include an analysis of the access latency distribution, misses per kilo instruction, or MPKI, memory stalls in the processor reorder buffer, system performance, and energy consumption. Before discussing these results, we present the experimental framework. This table shows the main machine parameters considered in the experiments. The conventional memory hierarchy consists of 3 SRAM cache levels, that is, private L1 instruction and data caches with 32 kilobyte 4-way each, and a 2-cycle access time. A private L2 cache with 128 kilobyte 8 ways and a 5-cycle access time, and an 8 megabyte 16-way 20-cycle L3 shared among 4 cores. In contrast, the proposed memory hierarchy where the FTC design is used consists of only 2 levels of cache. There's a private SRAM L1 instruction cache with 32 kilobyte 4 ways and a 2-cycle access time, a private FTC L1 data cache with a 150 kilobyte 4 ways and a variable access time ranging from 2 to 4 cycles. And finally, the 2L2 cache is an 8 megabyte 16-way and 20-cycle access time shared among the 4 cores. The proposed approach has been modeled in the cycle-accurate multi-to-sim simulation framework, and all the applications from the Spec CPU benchmark suite were run. Cacti and Destiny frameworks were used for the circuit-level models, providing timing, energy, and area numbers. This figure refers to the latency distribution in the cache hierarchy. Note that for FTC, latency in L1 is split into 2, 3, and 4 cycles, depending on the shift penalty. As expected, most benchmarks show a very high L1 hit latency distribution in both conventional and FTC approaches. However, a few benchmarks, like those highlighted in green, present a relatively low temporal locality as appreciated in the conventional approach. In these benchmarks, FTC boosts the L1 latency above 97%. By combining L1 and L2 levels into a single level cache, FTC alleviates the pressure in the memory hierarchy by filtering more accesses to the next cache level. Notice too that in applications like GCC, GROMACS, LVM, and MCF, FTC reduces the percentage of L3 hits with respect to the conventional scheme. In other words, the FTC hit ratio is higher than the combined hit ratio of L1 and L2 in the conventional design. This is mainly due to the conventional approach has duplicated blocks in L1 and L2 for an inclusive memory hierarchy, which reduces the effective storage capacity over FTC. In addition, FTC has a higher number of sets, 512, than the two-level conventional design with 384 sets, thereby reducing the number of capacity misses. On the other hand, in a few applications like B-Ways and games, FTC increases the number of L3 hits over the conventional scheme. This is due to FTC has less cache ways, that is 5, than the conventional combining L1 and L2, that is 12 ways. This translates into more conflict misses in the FTC. In summary, more than 70% of hits on average do not require any shift operation, with a lowest and highest two-cycle latency of 47% and 94% respectively. These results refer to the misses per kilo instruction, or MPKI. Note that the conventional approach distinguishes between L1 and L2 misses. FTC largely reduces the MPKI in benchmarks previously identified with a relatively low temporal locality. This is a consequence of an MTC with a larger effective storage capacity and less capacity misses. In addition, FTC reduces the MPKI in benchmarks with low memory requirements. Notice too that in a few benchmarks, both approaches show negligible MPKI results. This is due to the working set of these applications is so small that fits into the L1 cache. Overall, FTC reduces the average MPKI by 66% with respect to the conventional scheme. This figure quantifies the memory stall cycles in the processor reorder buffer. As expected, these results are highly correlated with the previous MPKI numbers. In particular, applications with a high MPKI show a large reduction of raw memory stalls in FTC. On average, FTC reduces the number of raw memory stall cycles by 45% with respect to the conventional approach. This figure refers to the speed up of the FTC and the state-of-the-art tape cache, focusing on L2 over the conventional approach. The blue line at 1.0 speed up means the same performance as the conventional cache. For the system performance, applications with a high MPKI or raw memory stall reductions are the ones with a higher speed up, surpassing at 30%. On the other hand, H264ref is the only benchmark where FTC shows a slowdown higher than 10%. This is due to the low locality exhibited by this application, where the two-cycle L1 latency is less than 50%. For the tape cache, results are similar as those reported in the original paper, where applications with a predictable L2 access pattern showed a speed up, but those with a less predictable pattern hurt the performance. In summary, the average speed up of FTC is by 15% over the conventional and tape cache designs. Focusing on energy consumption, this figure compares the consumption of FTC and the two-level conventional design. Energy is split into leakage and dynamic expenses. In addition, FTC includes the overhead of shifts. The energy savings of FTC in most benchmarks mainly come from the fact that FTC approach completely removes the L2 cache. However, focusing exclusively on L1 and FTC leakage, FTC consumes more energy because of the overhead of the larger tag array and higher complexity of the peripherals. Regarding dynamic expenses, they are higher in the FTC than in the L1 cache of the conventional scheme due to the same reasons as exposed for the leakage. Notice too that the dynamic energy in the L2 conventional hierarchy is rather low due to the serialized access to the tags and the target data way. The shift energy is only remarkable in a few applications where the overall energy consumption is slightly higher for FTC. The reason is that these applications account for a high number of shifts as a consequence of a low spatial locality. Overall, the average energy reduction of FTC is by 21% over the conventional design. To conclude, the size of current L1 caches is constrained due to the limitations of the SRAM technology. In this work, we have proposed to implement L1 caches with the much denser Racetrack memory technology. However, this technology imposes a variable access time due to the necessity of shift operations. To combat this downside, we have proposed the fast-track cache, aimed at reducing the impact of shift in L1 caches with a novel design and cache organization, preventing shift in more than 3 out of 4 accesses. Results have shown that the fast-track cache improves performance by 15% and saves energy by 21% with respect to a conventional SRAM cache design. Thank you very much for your attention.